Welcome students. Today we will study the chapter of wave motion. Wave is defined as the oscillatory disturbance traveling through a medium without change of form. During the propagation of waves, the particles of the medium neither leave their position forever nor they are carried away by the waves. These particles simply vibrate about their mean position when the wave passes over them. Every wave is a doubly periodic phenomenon. When a wave travels through a medium, it is observed that at any given point of the medium, the form of the wave repeats from time to time, which shows that the wave is periodic in time. Also, at any instant of time, the form of the wave repeats at equal distances, which shows that it is periodic in space. Thus, wave motion is periodic in time and periodic in space. Thus, it is called a doubly periodic phenomenon, or it is called doubly periodic in nature. The waves are basically classified into two types: progressive waves and stationary waves. Progressive waves are the waves which continuously travel in one direction, and the stationary waves are the waves which do not travel at all. They remain localized. We are going to study the stationary waves in detail in the next chapter. The progressive waves are further classified into two types as mechanical waves and electromagnetic waves. The electromagnetic waves are the waves produced by mutually perpendicular electric and magnetic field which are variable in time. Mechanical waves are the waves which need material medium for their propagation. Sound waves are mechanical waves. For successful propagation of mechanical waves, the medium must possess following properties. First, the medium should be elastic so that it can regain its original conditions such as shape or size, etc. after passing the wave. Number two, the medium should possess inertia so that the particles of the medium will store the energy while vibrating and transfer it to the successive particle after completing the oscillation. And number three, the frictional resistance of the medium should be small so that less energy will be wasted in overcoming it. Remember that frictional resistance need not be zero, otherwise the waves will never die out. It should be minimum so that less energy will be wasted in overcoming the friction and more energy will be conveyed to comparatively greater distance. Progressive waves are classified again into two types: transverse waves and longitudinal waves. Transverse waves are the waves in which the particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave. For example, light wave is a transverse wave. The second type of progressive waves are called longitudinal waves. The waves in which the particles of the medium vibrate in a direction parallel to the direction of propagation of the waves are called longitudinal waves. Sound waves are longitudinal waves. Now, before studying the wave equation, it will be important to study different terms regarding the wave motion. Very frequently used terms are amplitude. The maximum displacement of the particle of the medium from the mean position is called amplitude of the wave. It is denoted by A and it is measured in meter or centimeter. Second term is periodic time or period of the wave. The time taken by the particle of the medium to complete one oscillation is called periodic time or period of the wave. It is denoted by T and it is measured in second. Frequency. The number of oscillations performed by the particle of the medium in 1 second is called frequency of the wave. It is denoted by N and it is measured in hertz. Frequency of a wave is always the reciprocal of its period. That is, N is 1 upon T or T is 1 upon N. Regarding frequency, always remember that whenever any wave enters from one medium to another medium, its frequency remains constant. Wavelength. The distance between two successive particles having a phase difference of 2 pi, or the distance between two successive particles having same phase or same state of motion, is called wavelength. It is denoted by lambda, and as it is length, it is measured in meter or centimeter. Velocity of a wave. Velocity of a progressive wave is the distance traveled by the wave in 1 second. It is denoted by V and it is measured in meter per second. In one periodic time, a wave travels or advances through a distance equal to 1 wavelength. Hence, distance traveled is wavelength lambda and the time taken to travel that distance is periodic time T. Hence, V is lambda upon T, but 1 upon T is frequency N. Hence, V is denoted as N lambda, or V is obtained by taking the product of frequency and wavelength. Now, let us go to the equation of simple harmonic progressive wave. The waves which continuously travel in one direction are called progressive waves. If the particles of the medium propagating or passing these waves vibrate simple harmonically about their mean positions, then the wave is called simple harmonic progressive wave. Both transverse as well as longitudinal waves can be simple harmonic progressive waves. The figure shows the graphical representation of displacement of a particle carrying a wave along y-axis, that is, displacement is along y-axis with respect to its position from the origin along x-axis. The graph is drawn when the particle at the origin is at its mean position. When a progressive wave propagates through the medium, the particles of the medium are set into SHM. As the waves reach different particles at different instants of time, the particles of the medium are at different phases. Though wavelength, frequency and amplitude of all the particles are same, each succeeding particle lags behind the preceding particle. As the particle at the origin starts from mean position, equation of its displacement is given as y is equal to a sine omega t. We have studied this equation in the chapter of oscillations. In this equation, a is the amplitude or the maximum displacement of the particle from the mean position. Omega is the angular velocity. If delta is the phase difference between two particles, then consider particle A at distance x from the origin. As the wave reaches A after some time than O, particle at A lags behind the particle at origin in phase. So the equation of the displacement of the particle at A is given as y is equal to a sine omega t minus delta, where, as I previously said, delta is the phase difference. The negative sign of delta indicates that the particle at A lags behind the particle at O. This phase difference delta depends on distance x of the particle from the origin. We know that one wavelength distance is equal to a phase difference of 2 pi. So distance x corresponds to phase difference of 2 pi x upon lambda. Thus, delta is 2 pi x upon lambda. Hence, the equation can be written as y is equal to a sine omega t minus 2 pi x upon lambda. As 2 pi and lambda are constant, it can be also written as y is equal to a sine omega t minus kx. K is called phase constant and its value is 2 pi by lambda. Now we can substitute omega as 2 pi n and take 2 pi common from the bracket. So the equation becomes y is equal to a sine 2 pi into bracket nt minus x upon lambda. Now n is the frequency, which is the reciprocal of the period. Hence, n can be substituted as 1 upon t. Hence, y is equal to a sine 2 pi into bracket t by t minus x upon lambda. This is called equation of a wave because it gives displacement y of the particle at distance x from the origin. Now, substituting t, lambda or 2 pi n as omega, 4 more forms of the equation can be obtained. Thus, there will be 7 equations representing the same wave in different forms. As a part of CET preparation, it is necessary that the students should know all these 7 forms. When a wave is progressing, it has a certain velocity of propagation called wave velocity. It is given by the formula v is equal to n lambda. The particles of the medium are in SHM, so their velocity is constantly changing. It is called the particle velocity and it is given by the formula plus or minus omega under root a square minus x square. These velocities get affected due to reflection when the wave strikes different surfaces. There can be 4 important cases. First one is a transverse wave striking a denser medium. Look at the figure. When a transverse wave strikes a rigid surface like a wall, the wave velocity is reversed. That is, the wave will start traveling in the opposite direction. The particle velocity is also reversed because the particles of the rigid surface receiving the wave or the wave energy are not free to move. So, they reflect the particle velocity in such a way that their own resultant velocity remains zero. This is possible only when the particle velocity after reflection is equal and opposite to the particle velocity of the incident wave. Thus, both wave velocity and particle velocity are reversed. This creates a phase difference of pi radian between both the velocities. We know that there is a phase difference of pi radian between successive crest and trough. Thus, creation of a phase difference of pi radian means a crest is reflected as trough and the trough is reflected as crest. Look at the second figure. When a transverse wave strikes a rarer medium, the wave velocity is reversed, but the particles of the rarer medium are receiving the wave energy, and they being free to move, they actually start vibrating and the particle velocity is not reversed. So, a crest is reflected as crest and a trough is reflected as a trough. Now, the reflection of longitudinal waves is having some different mechanism. When a longitudinal wave strikes a rigid surface, both wave and particle velocities are reversed just as in the case of transverse waves. But if a compression strikes the surface, the wave velocity and the particle velocity of the incident wave are in the same direction. That is, in our figure, they are towards the surface. When the wave is reflected, both these velocities are reversed and once again become the same, that is, away from the surface. Thus, a compression is reflected as a compression. If a rarefaction strikes the surface, the wave velocity is directed towards the surface and the particle velocity is directed away from the surface. Due to reflection, both these waves are reversed, so the wave starts moving away from the surface and the particle velocity is directed towards the surface. Hence, the velocities remain opposite after the reflection also. Thus, a rarefaction is reflected as a rarefaction. Exactly opposite thing happens when a longitudinal wave strikes a rarer medium or rarer surface. When a longitudinal wave strikes a rarer medium, as the particles of the medium are free to move, the wave velocity is reversed, but the particle velocity remains as it is. Thus, when a compression strikes a rarer medium, wave velocity and particle velocity are directed oppositely. Thus, it is reflected as rarefaction. On the other hand, when a rarefaction is reflected, both wave velocity and particle velocity are directed in the same direction. Thus, a rarefaction is reflected as a compression. Now, let us study superposition of waves. When many waves are passing through a medium at a time, they do not affect each other because each wave travels as if the other wave or other waves are absent and it is traveling alone. When such waves pass through a common point in the medium, each wave sets the particle in SHM. So the particle is set into many SHMs simultaneously. Each wave produces its own displacement in the particle. So the resultant displacement is a vector sum of the displacements caused by the waves individually. Thus, all the waves pass through the medium without any modification or change in the characteristics. This is called superposition of waves. When two or more waves traveling through a medium arrive at a point in a medium simultaneously, each wave causes displacement of the particle at that point independently, such that the resultant displacement of the particle is the vector sum of the displacements produced by the waves. This principle is obeyed by all kinds of waves. The physical effect of superposition of waves is called interference. If the waves arrive in phase, the resultant displacement of the particle becomes maximum. This is called constructive interference. If the waves arrive out of phase, that is, having a phase difference of pi radian, the resultant displacement of the particle is minimum. This is called destructive interference. Beats is one of the best examples of interference of sound waves. When two waves of equal amplitude but slightly different frequencies interfere with each other, the intensity of the resultant wave changes between maximum and minimum. This alternate rise and fall of the intensity of the resultant wave is called the phenomenon of beats. The condition of maximum intensity is called waxing, and the condition of minimum intensity is called waning. One waxing and one waning is called one beat. The time between two successive beats is called period of beats. Number of beats per second is called frequency of beats. Now, when two waves of same amplitude A but slightly different frequencies N1 and N2 such that N1 greater than N2 interfere with each other at a point in a medium, the beat frequency is given by N is equal to mod N1 minus N2. That is only the magnitude of the difference between the frequencies. The waxings are repeated after equal time, and the period of waxings is given by T is equal to 1 upon N1 minus N2. Similarly, wannings also repeat after equal time, and their period is also same, that is T is equal to 1 upon N1 minus N2. Thus, period of beats is also given by T is equal to 1 upon N1 minus N2, and hence the frequency of waxings, wannings as well as frequency of beats is given by N is equal to mod N1 minus N2. The beats are heard only when this difference N1 minus N2 is less than or equal to 20 Hz. There are many applications of beats, out of which 3 are very important. Measurement of unknown frequency. With the concept of beats, or by producing beats, we can measure unknown frequency of any musical instrument. The unknown frequency of any sound note can be measured accurately by using the principle of beats. For this, the sound note of unknown frequency is sounded with another sound note of known frequency, which can be varied. Now, the known frequency is increased till beats are heard. Then, it is carefully varied to decrease the beat frequency to 0. In this case, the unknown frequency is same as the known frequency. With the principle of beats, the musical instruments are tuned. Tuning of musical instruments is very necessary to get the full pleasure of music. For better quality music, all the musical instruments are required to be synchronized in frequency. For this, one of the standard instruments, such as harmonium, is played. By changing one of the characteristics, such as tension in the string in case of sitar, the frequency of the other instrument is changed till beats are heard. Further careful adjustment decreases the beat frequency to 0. In this case, the frequency of the other instrument is same as that of the standard instrument. In this case, the instruments are said to be in unison. By using the principle of beats, very low frequency sound, especially the sounds of frequency less than 50 Hz, can be produced. In order to hear the beats clearly, the frequency of beats must be less than 20 Hz, or the difference between the two frequencies producing the beats should be less than 20 Hz. If the beat frequency is increased beyond 20 Hz, due to limitation of human ear, waxings and wannings cannot be heard clearly. If the difference between the frequencies producing the beats is increased beyond 20 Hz, the beats are heard separately along with the two interfering sounds. This is called difference tone. The principle of difference tone is used to generate sound of low frequencies. Superposition of waves and their interference can be demonstrated by Quink's tube experiment. The figure shows the Quink's tube. It consists of two U-shaped tubes ABC and PQR. Tube ABC has inner diameter slightly greater than the outer diameter of the tube PQR. Hence, PQR can slide in ABC. Tube ABC has two openings, S for the source and L for the listener. A source of sound such as a vibrating tuning fork is held near S and its sound is heard from L. Initially, tube PQR is well inserted in ABC. It is then slowly drawn out. The intensity of sound heard from L varies. The sound waves entering at S travel along two different paths, SBL and SQL. At L, these waves come together. If these two paths are of equal length, the waves interfere in phase at L. Thus, constructive interference takes place and a loud sound is heard. When PQR tube is drawn out, the path length SQL increases and the path difference SQL minus SBL is created. When this difference becomes lambda by 2, where lambda is the wavelength of the wave used, the waves interfere out of phase or with a phase difference of pi radian. Hence, destructive interference takes place and no sound is heard. If the tube PQR is drawn further, the waves again arrive at L with a phase difference of 2 pi or with a path difference of lambda. Hence, they constructively interfere at L and loud sound is heard. Thus, intensity of sound varies between maximum and minimum. Thus, this demonstrates interference of sound waves as well as constructive and destructive interferences. One of the most important effects of sound is Doppler's effect. The apparent change in the frequency of sound caused by relative motion between the source of sound and the observer is called Doppler's effect. The effect is applicable to all kinds of waves. As sound propagates in form of waves, it is applicable to sound waves also. If n is the true frequency of sound, v is the velocity of sound in air, v0 is the velocity with which the observer is moving, vs is the velocity with which the source is moving, and n1, n2, n3, n4 and n5 are the apparent frequencies. Following 5 cases are important. When the source is stationary and the observer is moving towards the source with velocity Vo, the apparent frequency n1 heard by the observer is given by the formula n1 is equal to n into bracket V plus Vo upon V. When the source is stationary and the observer is moving away from it with velocity Vo, the apparent frequency n2 heard by the observer is given by the formula n2 is equal to n into bracket V minus V0 upon V. When the observer is stationary and the source is moving towards it with velocity Vs now, the apparent frequency n3 heard by the observer is given by the formula n3 is equal to n into bracket V upon V minus Vs. When the observer is stationary and the source is moving away from the observer with velocity Vs, the apparent frequency n4 heard by the observer is given by the formula n4 is equal to n into bracket V upon V plus Vs. When both the source of sound and observer are moving with velocities Vs and Vo towards each other, the apparent frequency n5 heard by the observer is given by the formula n5 is equal to n into bracket V plus or minus Vo upon V minus or plus Vs. The upper signs should be considered when both are approaching each other and the lower signs when they are moving away from each other. When both source and observer are at rest, the apparent frequency is same as the true frequency. Similarly, when both source and observer are moving in the same direction with equal velocity, then also the apparent frequency is same as the real frequency. There are many good applications of Doppler's effect. 3 most important applications are: number 1, radar, that is radio detection and ranging. Radar system is used to detect aeroplanes. It is based on Doppler's effect. The radar antenna continuously emits electromagnetic waves in all the directions. When any plane comes in its range, these waves are reflected by the plane. these reflected waves are received by the same antenna. The true frequency of the waves is known and the source is stationary. So, if there is rise in the apparent frequency of the reflected waves, it can be concluded that the plane is approaching. With the help of the formulae, its speed also can be calculated. With the same effect and studying the spectral lines of the stars regularly, we can guess that whether the star is stationary or approaching towards the earth or moving away from the earth. The spectral lines from the star are studied regularly. If a star is moving towards the earth, the frequency of the spectral lines increases. So, they move towards violet end of the spectrum. On the other hand, if it is moving away from the earth, the frequency of the spectral lines decreases and the lines move towards the red end of the spectrum. By studying the rate of shift of the lines, the speed of motion of the star can be calculated. The shift in the spectral lines is called Doppler's shift. This is very useful for weather forecasting and for crop planning.